Yeah, so as Pratik already introduced the topic, so we are going to be talking about RobotPerf, which is an open source vendor agnostic benchmarking suite for evaluating robotics performance across different hardware. So essentially what we aim to do with RobotPerf is create this benchmarking suite which is firstly vendor agnostic, therefore it is also architecture neutral, and it can test robot hardware, so compute like what let's say Niladri's company provides to uh, so Intel, AMD, all of these guys, whatever compute boards they provide, how do you see what their performance is like for, let's say, a localization task or for a manipulation task? That's the aim with RobotPerf. One thing I would like to note here that RobotPerf is essentially a work done by a consortium of organizations. We have Harvard working with us, we have CMU, we have Ford, AMD, also Intel working on this benchmarking platform with us. So before I get into the details, like as I said, why do you need benchmarking at all? So benchmarking essentially, let's go with the definition here. Benchmarking essentially means that you define a standard set of tasks, and then for a certain period of time you measure how those tasks perform on a certain compute board. That may be, let's say NVIDIA Jetsons, that may be AMD Krias, that may be Intel Agilex also. So that's the aim with benchmarking. And how does that help you? So essentially, it firstly helps you choose optimal hardware for robotic applications. There may be situations where, let's say for a perception task, the Jetsons may work the best. For, let's say, a control task, or as Niladri mentioned, for, let's say, model predictive control, you would probably prefer an FPGA solution. So to get that, to have that as a visual representation, to have those metrics with you, is why you need benchmarking. Then apart from that, so compare different algorithms we've covered. Evaluate performance across ROS2 versions. So there may be situations where certain features of ROS2 itself are deprecated in a future version. So you need to have a measure of that too. So that is something that benchmarking will help you with. And therefore, all of these things put together help you prioritize your future development. So it's not like, especially as your company grows larger and larger, you can't have that, let's say the quick iteration cycle of a startup where you can switch a board and things are going to remain the same. The iteration cycles as you grow larger increase a lot. So hence you require a benchmarking suite like RobotPerf to give you those metrics. Now the challenges in robotic system benchmarking is that everybody, like as one of the questions was asked, that everybody has a different way of, let's say programming the board itself. Intel has its own suite, AMD has its own suite, NVIDIA has its own suite. How do you ensure that, whatever you're benchmarking is not affected by the capabilities of the suite itself? That is one of the challenges. And therefore, you need a architecture neutral, representative, and reproducible benchmark. So given that, what we've done is we've used ROS2 as the benchline for our benchmarking. So that is where, the baseline for our benchmarking. So this is essentially what the standard, ROS2 stack looks like. What we are focusing on, I hope everyone can see this. What RobotPerf works on is essentially the middle block, where we test the computational graphs of various hardware and see where are they. We just benchmark those metrics. So you can see over there that we also, because we want to be hardware agnostic, there's CPU, FPGA, GPUs, and we also want to add support for further accelerators. What I mean by other accelerators are, let's say, machine learning accelerators that exist right now. TPUs also maybe in the future. So we have space to account for those hardwares also. Now, how RobotPerf works is essentially based on two very core foundational contributions to ROS. One, on the left that you see, sorry, the right, I'm not sure. The one with the 9 dots logo is the ROS2 tracing. It's essentially, let's say, a ROS package which has added tracing functionality in your ROS2 stack. It's available in Humble and Rolling as we speak. And what it does is, I should probably explain what tracing means. That tracing allows you to add trace points in your ROS package and helps you see how interaction with the compute hardware itself is happening. So that's ROS2 tracing. The another side of things is robot core framework. The robot core framework essentially helps create trace tools for vendor specific tools. That's one of the things that the robot core framework allows for. And there's a certain open source aspect to this, which is REP 2008. REP stands for ROS enhancement proposal. So that essentially is, allowing for you to, we've added features to the ROS2 stack where you can essentially switch easily between any kind of hardware accelerator tool that's available. So these are the two things which help us essentially deliver RobotPerf as an open source tool to everyone. So now with regards to, fine, I've defined benchmarking, I've defined how we go about it. Now the thing is, what are we exactly testing for? So when it comes to performance testing, there's two things. One is functional performance testing and the other aspect is non-functional performance testing. Just to quickly give a brief overview of what these terms mean. Functional performance testing is essentially that you're looking at whether the certain implementation that you've done is it achieving the goal that's needed. So let's say you're taking a motion planner. So you are essentially measuring, okay, what's the failure rate like of my motion planner? If you're taking an RRT or if you're taking an A star or a suboptimal A star, what are the failure rates like? That's what you're testing with functional performance testing. With non-functional performance testing, what we are looking at essentially is the system characteristics. So your energy consumption, your latency, your throughput, those are the things that we are measuring of, let's say, the compute hardware or the entire system. So that's functional performance. These are the two things. With regards to RobotPerf, given what the aim is, we are currently focusing on non-functional performance testing itself. We are looking at what are the characteristics of the compute hardware itself with regards to certain ROS packages. So that's one of the founding principles of the RobotPerf benchmark. Then we are looking at, as I said, we are looking at latency, throughput, and power. These are the three characteristics that we are measuring of each compute board. And I'll just quickly run through what these terms means. Latency, essentially that from start to end, how much time is, let's say, your system taking to complete complete whatever task is at hand. Throughput essentially is the number of computations that your that your system can do for a given period of time. The more, the better. And power is essentially the energy consumption of the system itself for a certain task. So this is what we are measuring. Yeah, okay, sorry. So with regards to flexible methodology, there's two ways to measure system performance. One is black box, which sort of aligns with, that you don't have, let's say, access to the internals of the system. So things like energy consumption and throughput are not easily measurable. So we have support for both of these methodologies. Black box is you're essentially looking at, okay, this is the input to the system, this is the output. So I'll probably get a measure of latency and failure rate. With gray box, you are going within your system and looking at other characteristics like throughput and energy consumption. So we have support for both of these methodologies in the RobotPerf suite. With regards to adaptability, yeah. So essentially, one of the reasons that we did choose ROS2 as the baseline here for RobotPerf was the fact that ROS2 makes it easy to compose the graphs that you see at the bottom. So it can simply, if you have to just create multiple nodes and they have to be interconnected, and that construction is very easy, and that's essentially a feature of ROS2. So that's why it was chosen as the baseline here. And then another aspect that we wanted to focus on was reproducibility. Now, there are obviously other benchmarking tools that are available, but the thing is, reproducibility also means that you have to buy into the kind of data format that they have. Now, given that we are a ROS2 centric company and it's an open source tool, we chose for the data sets that we have ROS bags as the format. So we will have ROSBAG support, and in the future we will add, let's say, MCAP support also. But we want to move to the data format that the community is most comfortable with. So yeah, that's essentially covering that. And portability. So with regards to, sorry, yeah. With regards to portability, as I said at the beginning, that we are not focused on a certain kind of, let's say, hardware accelerator. It's not just going to be, let's say, GPUs only, or it's going to be FPGAs only. We want to add support for multiple accelerators, and yeah, so it would be machine learning accelerators or ray tracing accelerators, anything of that sort. So as it's an open source effort, we obviously encourage anybody, if they're working on a certain kind of accelerator, to join this effort and contribute to the benchmark. Now let's come to the interesting aspect of this, that, okay, what do the results actually look like? So before we get there, let's look at what we've tested. So as I stated in the beginning, we have tested for perception, localization, control, and manipulation. These are standard, let's say ROS2 packages that are available, and we've used them, we've leveraged them as the baseline so that the community also can test it on their own hardware. These are popular packages within the ROS2 ecosystem. So it's not like we are creating a new package and testing it for a certain hardware. It's all easily accessible for anyone to, let's say, test their hardware on. Now, what do the results themselves look like? So what would be the, let's say you want to contribute to RobotPerf and you've benchmarked the hardware. We essentially output all of the results in the form of these polar plots. And you will see that there is a certain kind of color coding here where the darker colors essentially represent black box testing, and the lighter colors represent the gray box testing that we've defined. And it's basically, for multiple hardware platforms, and you will see that there is this C1, C2, C3, or even A2, A3. They are just our code, code representations of the various packages that we've tested. This is available on our documentation. You will see what the codes represent when it comes to the ROS2 packages. And now, what did we do with regards to what was actually published in the paper that we are in the process of publishing? Is we've basically benchmarked 18 different platforms that you will see over here. The general categorization here is general purpose hardware. So you'll see essentially it's CPUs over there. Then there's heterogeneous hardware. Heterogeneous implying essentially a CPU and a GPU mix, or a CPU and an FPGA mix. Then there's obviously reconfigurable hardware, which is where Kriya or Agilex and all of these fit in. And then there's accelerator hardware. By accelerator hardware, we mean that, okay, you do have, let's say, a reconfigurable or a GPU there, but now you've written a, let's say, accelerated package that you want to test on it. So we've got that also. And in conclusion, what do these, let's say, results look like? So one of the things that I want to, let me go to the next slide. So yeah, the takeaways here with regards to what this benchmarking does is 3 key points that we have to remember. One is it's a quantitative approach to hardware selection. So you do know when you're, let's say, you're a young robotics startup, or you're a larger robotics company and you want to test 3 different kinds of hardware platforms that are available. You will have these benchmarks accessible to you to see that, okay, yes, let's say some X board has this sort of latency for a manipulation task. I am a manipulation company. Let's not go forward with this. So that's one thing. Then representative assessment of heterogeneous hardware. So as I said, that we want to add support for as many platforms as we can. So that's why we've chosen ROS2, because first we have to get access to you have to write the ROS2 API for certain accelerators that currently don't have it. And then you can push that into the ROS2 ecosystem for everyone to look at the results. And lastly, which is assessment of acceleration benefits themselves. So sure, you may have accelerator hardware available to you, and now you want to optimize it in a much better fashion. So how does that happen? So a visual illustration of that is what we see over here. We've done a test with the AMD Kriya KR260. So that's a FPGA solution that's available by AMD. And then we've got the benchmark results there, which you can see. And then we've added robot core perception to it, which is one of the IP cores that we have. And we've tested the results for that. So you have a clear-cut, let's say, a visual representation of whether your acceleration efforts are working and what is the current baseline that you have with a certain accelerator product. So that's essentially what this enables you to do. And now, in conclusion, I would like to say that I would highly encourage everyone in this room and across the cross ecosystem to join this effort. It's currently represented by all of the people that you see on the slide. there's people from, as I said, Harvard. One thing I would like to note here is that this work, a significant contribution of it, comes from the Edge Computing Lab at Harvard. Uh, this is led by Vijay Janappa Reddy. He is particularly famous for also chairing the ML-Perf effort, which is a performance benchmarking system for machine learning. So he's continued this work with us in RobotPerf. So yeah, that's the conclusion of it. The QR code is just for the ROS2, for the GitHub page that we have. And yeah, I'm open to questions.
So we can have a few questions. Any questions? Yes.
Hi, Gaurav. Thanks for providing the details. So my question is goes around which one is good, FPGA or the which vendor you will say now, Qualcomm or Nvidia?
I mean, that's a great question, but it's not in my interest to answer it. So I won't do that. But what I'll say is, with respect to this, with respect to what this effort is, you should be able to see the results for yourself. With all the benchmarking that we do, it's pretty explicit like what hardware would be better for what kind of application. So yeah, I'll leave it at that.
So other thing I want to ask is like how you are ensuring that the generated code or who has written that, like FPGA, maybe the one you are testing. So
Right.
how are we ensuring that that is written correctly? Maybe it is not utilizing the right libraries. So do you have the data about it or anything like that?
So on the application layer side of things, we are essentially using standard ROS2 packages. So there's nothing that, like it's widely used by the community. And one of the reasons that we used ROS2 packages was that the community can themselves see that, okay, probably this is not the best implementation for this kind of task. So an improvement can be done. So the reason that this has been kept open is that the community can themselves come forward and say that, okay, this is not probably the best benchmarking tool, the benchmarking package that we should use. We should probably switch to something else, and this is what it is.
Thank you.
Any other questions? Yes. So do we have any other robot performance test for microcontrollers that are on the lower level stack of the robots?
Like when you say microcontrollers, could you cite an example?
For example, for our robot applications, we use NXP's IMX8 microcontroller,
Right.
just something similar to what Teensy has. So if there's any RobotPerf's performance test for that, so that we can evaluate, so that we can do some advanced PID control, like what yesterday we discussed, like the model predictive control and those things,
Right.
using some tiny ML models within the MCU itself. So without just pushing those data to the higher level
Right
stacks.
now we don't. Right now we haven't included NXP solutions in this.
Okay.
I'm not sure about their ROS2 API situation. So yeah, they
So
are
we
currently
are also
there.
working with the micro ROS agent. So we have a different type of topology. My ideology is to actually use the MCU itself for these kind of model predictive controls and all those implementation. So
Right.
for that research, we need some performance tests to evaluate the MCUs that we use. That's the reason.
I mean, if you have a group, I would just ask you to you can just send a pull request or raise an issue, and then the community would jointly serve that problem.
Yeah. I'll do it. Thank you.